Yeah, so I'll be given a little bit of an overview of what we do at the University of Florida and how we meet the demands of our research computing environment with HiPerGator 3. That's our supercomputer, or the latest version of it, and the DDN storage. So let me start by giving you a short overview of the history of how we built a supercomputer center and support research computing. So we started in 2004, where we actually started very small, and it was driven by the CERN, Large Hadron Collider. We had a strong physics group that was working on that. They had some funding from DOE to try and build out infrastructure that needed to be ready by the time the Large Hadron Collider was going to turn on around 2010. And so they approached the leadership at the university, and we started to build a data center. Then in 2011, the University of Florida hired a CIO, and his name is Elias Elderi, and he had the vision that a university like the University of Florida needed a much more robust research computing infrastructure for all the research that was going on, because he sort of saw that it was going to grow in data and in compute capacity. And at that time, I was hired as the director for research computing. So we constructed in 2012 a data center, and that's when we built HiPerGator 1. We actually did a contest across the university with all the students providing input on what are we going to call the University of Florida supercomputer, and we came up with this name called HiPerGator, spelled in this funny way. And once we had that name, everybody thought that there was no way we were going to come up with as good a name. Everybody really loved it, which is why when we upgrade systems, we keep the name and we just attach a version number like with software. So the HiPerGator 1 was the one in 2013. In 2015, we upgraded it to HiPerGator 2, and then in 2019 we planned, and in 2020 we constructed HiPerGator 3, and it became operational in January of 2021. And during that time we also saw increasing need for storage, and that's where we started a very long and successful partnership that just kept growing over the years. Initially, we've been working with Lustre for a very long time, but then we really started to focus on DDN. Initially, we did some growing it of our own in 2004, but in 2010, we basically had a SFA 14K, and in 2019, we expanded them and replaced them with 18Ks. So one of the goals that we had is to have these multiple generations of systems and all the different storage systems be visible to the users as a single system. What we've learned is that users don't want to deal with details of, I'm submitting my job, I want it to start as quickly as possible. Should I go investigate and gamble that it's going to run on this cluster or that cluster or this file system, or do I have to move data around? They just want it to work. And actually the main thing that we've learned is over the years is that users, they want to submit a job and they want it to start as quickly as possible, because the worst that, as far as they're concerned, is that you submit it and then you have to wait for hours or days, and then there happens to be some kind of a mistake in your script, and after a second or so it dies, and then you have to start it over again. They just want to know they submit it, it starts, and then they see it's running, and then they can go do whatever else they want to do. So they like it to be a unified system. So the way we have sort of grown our system, we have some public login nodes, and then all the different HiPerGators or different versions are sort of integrated, and they all see the same storage systems. They're all connected with InfiniBand and Ethernet. And the evolution is that initially HiPerGator 1 was 16,000 cores. That was available from 2013 all the way to May of 21. That's when we turned it off. In HiPerGator 2 was an expansion of 30,000 cores that is still running, and we plan to turn it off in 24 or the end of 23. And then in HiPerGator 3 was added the latest, and we changed from AMD for HiPerGator 1, Intel HiPerGator 2, AMD HiPerGator 3, and that works fine for most of the users. It's absolutely no problem. And then in 2020, we basically got a donation from NVIDIA. Chris Malachowski, one of the co-founders of NVIDIA, is a graduate from the University of Florida 30 years ago, and he really loves his alma mater, and he basically approached our provost and said, what would you do if I gave you a superpod? And the provost said, well, we're going to create an AI university and basically make sure that every student who comes through the University of Florida is going to be educated as a citizen and know about AI. That doesn't mean we're going to turn all of them into engineers, but we're going to turn all of them into people who know if they have data and a question, how can AI help? What can AI do? What can it not do? What are the ethical and legal implications so that they can be knowledgeable citizens and not fall, to some of this overhype or underestimation or whatever, so that they can make good decisions. And so that really accelerated our entire university, because when we started in the beginning of the past decade, there was a reasonable assumption that if somebody wanted to use an HPC system, they knew what HPC was. And they just came to us, and they needed some technical help, but they mostly just wanted an account, a command line, a window, and off they went. Now we have people who have data, and they have a question, and they say, well, I've heard that AI can help me get the answer to my question. And so we now have expanded our staff to really help people train and learn about and help them develop their workflows so that they do get answers. And we teach students. We teach like 60 classes every year now. Some of them have just 25 students. Some of them have 150 students. And one of the things that we saw in the 2 years is that our data storage has grown massively. People have bringing in data. We have 3 flavors of data. The first one we call Blue, and it's high performance storage. It's a SFA 18K, and it has 300 terabytes of NVMe, and it's a total of 7.2 petabytes of spinning disk. And that's our high performance. That's where people do their main calculations. And then we have the orange capacity, which is a similar system, but it's configured differently. It doesn't have the big NVMe cache, and it has fewer controllers and more spinning portion, but it's 16 petabytes. And that 16 petabytes grew over the last year from 3 to 16. That's how fast the growth is of data that people are bringing in. And then we have the red file system, which is a AI 400. That's connected to the SuperPod, and that's where we have the extreme high performance stuff. We also have a secure Enclave that is currently storing its data on the Blue storage system, and it uses encrypted virtual disks. So we have virtual machines that access virtual disks, and these virtual disks look like files on the Blue file system. And that allows us to have like absolute security. There's nobody, not even the system administrators, that have access to the data of our researchers. One of the things that we've learned, though, it's a challenge that we're trying to address now, that is that the intense I/O that happens on the high-performance computing part of HiPerGator sometimes causes delays on the Blue file system that for those virtual machines is not acceptable. So now we're developing a separate file system to meet this challenge. And we haven't found an answer yet, but we know we have to separate it out because the 2 user communities and the different I/O patterns don't mesh well. So to give you an idea of our users, we have 500 groups Typically, each group is led by a faculty member, and the faculty member has a group of researchers that are undergraduates, graduate students, postdoctoral associates, or remote collaborators from anywhere in the United States or in the world. And that then comes out to be a total of 5,000 users. And the community that we support is very, very broad. We basically do everything that you can imagine. We support 1,600 applications, and if you include the different versions of the software, it goes up to 2,500 different versions. They're managed by a module system so that users can pick the version they want, and then we sort of have a process whereby we make the next version available and then tell people about it, and then at some point we switch that new version to become the default version, and then we go back and change that, and then we keep some of the older versions so that people that cannot migrate to the new version for whatever reason can still keep on working without interruption, but we keep moving the system forward. So the way we manage our resources is by portraying our system not just as a sort of a queuing system. We give people a virtual cluster. We ask people, tell us what your needs are on a constant sort of basis. How many CPUs, GPUs, and storage would you need in order to sustain the daily activities of your group? And then you buy an allocation with that size. And our system is now large enough. We have currently 70,000 CPU cores, 1,800 GPUs, that we can basically guarantee that if a group wants to get access to the CPUs and the GPUs they bought, they can just issue a request for an interactive session or a batch session, and they get it satisfied within one Slurm scheduler cycle of 90 seconds. So what they need, they can get. And the reason it works is when you have 70,000 cores, even if the system is running at 90%, there are 7,000 cores idle. And so that if somebody has, need access to their 128 cores and they haven't been using it, they can just make a request, and out of the 7,000 cores, the Slurm scheduler can find them and just give them right away in the next cycle because they're available. So that's what we found years ago when we had a very small cluster. We constantly had to fight with our user community on how to get to the top of the queue, and we had to come up with ways that no scheduler could ever satisfy because the faculty came up with rules for why this person needed more priority than this other person. If you don't have enough resources, you don't get it. If you have enough resources, then you can satisfy everybody. And we're not doing it for free. That was another thing. If we make people pay, even though it's a highly subsidized rate, but if you make them pay, then they don't go overboard and ask for everything, because there are always some users in chemistry or materials engineering or gene sequencing that if you give them any computer, they can fill it forever with no problem if it's free. But if it's not free, then they sort of think about it and say, okay, this is what I really need. I have funding for this project and I need to get it. Now we do have a mechanism that once you buy in to our cluster, then you can also get access to idle cores by putting it sort of in the background burst capacity. And so you can put it there, and then if there are idle cores available, the system will allocate them and you'll get it run. And there are some faculty who train their graduate students to make sure that everything they have, plus all the burst capacity they have access to, is used 24/7. And if any of their students are not submitting jobs, the faculty get after them and say, hey, you're letting our allocation go idle. That's not allowed. So anyway, that is the way we manage our system. So the typical workflows that we need to support goes like follows. So users connect to the login nodes, and if they don't want to connect to the login nodes, which is typically a command line access, we have Open on Demand, which is an NSF supported interface, web browser based, developed by Ohio Supercomputer Center, that is really useful for people who just want to have an interactive view of the world. So they go in their browser, they can connect to HiPerGator, and then they get presented with the kind of applications that they can click on and say, okay, I want to start this application. They don't have to know anything about Linux or whatever. They can just run their application and it shows up in their desktop. And all the graphics acceleration gets done on the remote servers, so they can do it from any remote laptop or desktop, and they can even do it through slower connections, like if they're in a hotel room and the connection is not that great. Since the only information that's being sent back and forth is the actual image, it actually works quite flexibly, and it also allows us to avoid problems of users trying to do something and there's something wrong with the way they've configured their endpoint configuration, and that causes some weird problems with some applications that don't work. And this, we just make it all work on our system, and then they can connect to it and it works perfectly fine. So that works good. Another way that users are accessing it is through web portals, and that is, as everybody is recognizing across the world, is really a new way to engage with a much larger community. You have a web portal, and Galaxy is one example that started with this in gene sequencing first, but now there are more and more. And we now even have research group specific ones. So if there's a particular research group, they say, we have this community, it's part of our NSF grant or NIH grant, and we have all these collaborators, and we want to make some of our data available, and then we create a portal. So that's one of the things that we are developing that didn't used to be sort of part of traditional HPC, where there is HPC being done, but you also have to make the data available through a nice interface, and then we work together with the researchers, and they are the ones that maintain the details of that website, but we provide the infrastructure for it. And all the resource calculations is done by Slurm, our scheduler. So typically, the steps are, first you have to get some data, and people contact us and we help them find the right way to go about it. And we have a Globus license so that people can get transfers from all their colleagues, and that all works very efficiently. That works very well. Then there is a stage where people do computation, which can be various things. Some examples are gene sequencing, materials modeling, machine learning, of course, is now a big deal. And it's both the training part, which is very compute intensive, and then the inference part, which they often want to make available through a web portal so that their larger community can use the results from whatever their project is. And this is often a requirement from the NIH funding or the NSF funding, is that you have to make your results available to the public, or at least to a larger community. So they can make that with authentication or without authentication, then it's general public. Image processing and analysis is now also often used, and that all requires a lot of data, and that it gets handled very well by our DDN infrastructure. And then you present the results, like I said, in publications, but increasingly people want to have the results available, and funding agencies are requiring it to make it available through web services. So where do we get some of our demands? So we have a large number of users, and when we really look at it, there is no or very few sort of big I/O patterns that you see. Like I said, we have 500 different groups. Each group has a slightly different workflow, and there's 5,000 users, and essentially what the DDN exascaler system sees is just random I/O. You know, even if there is a person who has a very carefully crafted MPI calculation going with MPI-IO configured or whatever, they are just interspersed with a lot of random I/O. And that's where our all-flash cache in front of the SFA18K in the blue file system is really important and makes a massive difference. And also some of the latest examples that latest enhancements that EXA5 brought, like data on metadata, that has been huge. We've been struggling with small files because these gene sequencing people, they basically run something, and other bio applications, they run something and they create like 1 million or 10 million or 100 million files in like one swoop of an hour. And in the old system, that was really bad. Now, with data on metadata, all these files are tiny, and basically the metadata server has all cache disk, all NVMe disk, and when people make a request to the exascalar file system, give me this file, or create this file, then the first 64K of the data is like right there. So instead of having the old Lustre protocol where you make a request to the metadata server, and it tells you this is where the data is, and then you make another request to go get the data. In this particular case, you say, where's this file? You basically get the answer back, this file is here, this is where all its data are, and by the way, here's the first 64K. So if your file is like 4K big, which many of these files are, then you're done. And the performance is just massively different on the whole system. And then another thing that is a great feature is progressive file layout, because that allows the system to direct how to grow a file, and in a way that its performance is sort of consistent when the file gets bigger and bigger. We always try to explain to the users and try to train them, you can specify how to optimize the file layout, and there are all these parameters that when you create the file, but nobody does that. Nobody has time, and the graduate students don't learn it, and so now that the EXA file system does this automatically, it makes our life a lot better, and it makes them and more efficient, and the system just runs a lot better. So this is great. And so when we look at the majority of our files, 90% of our files live in this 300 terabyte of flash, and it works just great. So now the secure enclave issue that we were talking about, we have these secure virtual machines that write these encrypted virtual drives, and so they cause a problem because the virtual drives look to the file system as a big file. So when the virtual machine is writing in there, you basically are looking at a lot of very small IOs that are making sort of random changes inside that big file, and that doesn't work very well. So now we are working on having a separate file system so that we can optimize the IO pattern for that kind of system, and it works well. So the EXA file system and the SFA 18K works fine when it's all by itself used for this kind of pattern, but when you mix it in with all the other random I/O, it causes delays that are not acceptable to some of these virtual machines. Especially Windows is very delicate about how fast you get an answer back. Linux is much more stable, but Windows is problematic, and we need to support both. So the next, another thing that is happening in the last couple of years is with this big breakthrough of AI, where everybody is now trying to use AI, there's a lot of research communities that are sort of seeing the final realization of the dream of big data. So in the last 20 years, people have been collecting large amounts of data because sensors are simple or cheaper, they're ubiquitous. So people are collecting large amounts of data, and the vision always was that data is going to help us get all kinds of answers, learn all kinds of things about patterns, like more accurate prediction of weather, more accurate prediction of crop. At the University of Florida, we are an agricultural school, so we are very interested in all kinds of crop management and disease management of crops in the state. We have offices in all 67 of the counties of the state. But what happens is, with that large amount of data, if you ask people to look at the data and find these patterns, then you get some interesting things that you can, after a couple of years, when a graduate student or an undergraduate student works on this, they can have a publication and say, oh, that was interesting to know. But that's not going to help the farmer to sort of save their crop. Like if there is some disease starting in their crop, you want to make sure that in the first couple of days when this little patch of bad citrus develops in a corner of their field, you want to have something telling you, hey, that corner of your field is infected, go and do pesticide X or cut out that tree or whatever. You can't wait until half the crop is done. So you need to be able to answer within 24 hours. Well, this is where AI comes in. If you have all this massive amount of data, then you can do AI on it, get an answer, and get an answer back to those farmers who reported that they see some weird stuff happening. Or you can see it from satellite images, from drone overflying. Again, AI is massively helpful. But also precision medicine has been the same. We have massive amount of data about patients and the patterns of what they do. But in order to really get to this dream of precision medicine and personalized medicine, you need to be able to correlate data that is now protected. Because if you de-identify the data, you can get all kinds of general trends. But if you want to find out, well, what's wrong with patient X? Well, you want to be able to sort of say, well, patient X was seen in the office by the doctors on these and these dates. So one of the de-identification mechanisms that people use is change the dates of when they visited. But if you want to do precision medicine, you want to be able to correlate, they were seen on these days, and those were the days where the UV index in the cities where they live was higher. And so you need to correlate the date exactly where they lived. You have to have their zip code. And now HIPAA starts to say, hey, that is protected information. And so the doctors want to do all their big data, and they want to mix some of the public data, like what was the weather across Florida, with individual information. And so we've been under the request of making our high-performance computing system available for PHI. And so we've engaged in a high-trust certification process to make that possible. So that is one of the challenges that we are facing. And this is where there is an interesting feature that we are eagerly awaiting to deploy with EXA6, and that is encrypted directories. Because as part of HIPAA, there is a strong recommendation that you need to have your data encrypted at rest. And in the old days, when you had individual servers, it was perfect, and desktops, it was perfectly sort of acceptable to say, hey, we have hardware encrypted at the disk, so when the doctor or the nurse leaves at the end of the day, they turn off their computer, it's done. But something like HiPerGator is running 24/7. You turn it on and it never stops until you turn it off forever, right? I mean, it runs 5 years continuous, so it's never at rest. And the real original notion of having encrypted disks or at the hardware level was if people came and stole the drive and then put it in some other computer, they could reconstruct the data. So that doesn't happen anymore. And what this EXA6 feature allows is that you can do encryption at the directory level. So basically the entire file system is not encrypted at all, but a particular project can be encrypted, and if that particular project doesn't have any members that are active, then they can, it's going to be encrypted and nobody else can see it, and only when they're active does it get decrypted. So that's an interesting feature that we're waiting to deploy, and that's it.